At first, the problem looked ordinary. 3 cities separated by water, a connection that, on a map, seemed almost inevitable. But the moment engineers began tracing possible routes, one fact became clear: land was unusable. Every coastal alignment, the logical, cheaper, historically proven solution, collapsed under constraints before design even began. Not because the distances were too long, but because the coastline itself had become untouchable. Shipping corridors cut through it like arteries. Aviation zones hovered above it. Environmental protections locked it in place. Political boundaries froze it permanently. The usual engineering question, how do we cross this water, was replaced by a far more restrictive one. Where are we even allowed to exist? The Pearl River Delta is not open sea bordered by empty shores. It is one of the most congested maritime systems on the planet. Massive container ships move through fixed navigation channels that cannot be shifted, narrowed, elevated, or interrupted. Any bridge that stayed near land would have to pierce those corridors repeatedly, forcing ships to slow, divert, or accept permanent risk. That option was rejected outright. Raising the bridge higher did not solve the problem. Taller spans demanded heavier structures, which demanded more foundations, exactly where foundations were least stable. The delta's seabed is layered, compressible, and constantly reshaped by currents and sediment. In this environment, adding more supports didn't increase safety, it increased unpredictability. The more engineers tried to adapt shallow water bridge logic, the faster it broke down. And then came the limits no equation could soften. Separate legal systems, airspace regulations, international maritime rules, none of them negotiable, none of them flexible. These were not design challenges, they were hard boundaries. By the end of the earliest studies, the conclusion was no longer debated. If this connection was going to exist at all, it could not cling to the shore. It had to move outward, into deeper water, stronger winds, heavier waves, and conditions that bridges are not normally asked to survive. The sea was never the preferred option. It was the only remaining one. And by choosing it, engineers didn't simplify the problem. They stepped directly into something far more dangerous. Once the route was pushed offshore, the project entered territory where traditional bridge logic stopped being reliable. On paper, long-span bridges are designed to dominate distance. Suspension systems, cable-stayed towers, and aerodynamic decks have crossed wide waters before. But those designs assume something critical, that wind, waves, and foundations can be treated as mostly separate problems. In open sea conditions, they cannot. Out here, wind does not act alone. Waves do not arrive independently. They interact, reinforce each other, and generate complex motion that travels through the entire structure. Vertical wave-induced movement feeds lateral wind oscillations, which then reflect back into the deck and towers. The system never truly rests. For a suspension bridge, this creates a problem no amount of stiffening easily solves. Increased stiffness and loads transfer directly into foundations that are already unstable. Increased flexibility and oscillations grow faster than damping systems can absorb them. The bridge becomes dynamically alive, and not in a controllable way. Then there was the problem no bridge engineer wants to quantify too closely: ship collision. Near the coast, piers are threatened by small vessels. In the Pearl River Delta's offshore lanes, they face ships weighing hundreds of thousands of tons, moving continuously, day and night. Even a low-probability impact event would be catastrophic, not just structurally, but economically and politically. Designing piers to survive that scale of collision would require massive dimensions that would disrupt currents, scour the seabed, and amplify foundation instability. The structure would become safer in theory and more dangerous in reality. And beneath all of it lay the depth problem. In shallow water, foundations behave like known systems. In deeper, softer layers, they do not simply become taller piles. Each additional meter penetrates less predictable soil, where stiffness varies laterally and vertically. Instead of uniform support, foundations begin to behave independently. Loads stop distributing evenly. Small differences turn into long-term movement. At that point, the failure mode isn't collapse, it's divergence. One tower settles slightly more than another. One pier rotates imperceptibly faster, and the bridge, designed as a continuous system, begins to fight itself. Before construction ever began, engineers reached a quiet conclusion. The problem wasn't span length, or material strength, or even cost. It was that open water had changed the rules, and the existing rulebook no longer applied. With coastal routes eliminated and traditional bridge systems failing offshore, the project reached a moment engineers rarely admit to publicly. Every remaining option made the problem worse before it made it better. The most critical decision was also the most counterintuitive one. Instead of pulling key structural elements closer to shore for stability and access, engineers pushed them farther out, directly into open sea conditions. This was not done for elegance or efficiency. It was done because no surface structure was allowed to exist where global shipping needed to pass freely. By relocating critical sections offshore, the alignment finally avoided the densest navigation corridors. But the cost of that freedom was extreme. Construction platforms now sat in deeper water, exposed to waves, tides, and weather windows measured in hours, not days. Every operation became time-critical. Every delay multiplied risk. Logistics stopped being a support system and became a structural constraint. At the same time, foundation design began to fail in a different way. Board piles, normally the most reliable answer for heavy loads, reached a point where uncertainty arrived before structural capacity. The piles could theoretically carry more weight, but engineers could no longer guarantee how neighboring foundations would behave relative to each other. Variability, not strength, became the limiting factor. The structure was strong enough. The ground was not predictable enough. Then came the realization that forced a fundamental rethink. Even if a surface bridge could somehow survive wind, waves, collisions, and foundations, it would still permanently obstruct some of the busiest shipping routes on Earth. This wasn't a temporary inconvenience, it was a long-term global constraint imposed by a single piece of infrastructure. That outcome was unacceptable. In that moment, the project crossed a threshold. It was no longer a bridge design problem. It was a question of whether a bridge was even the right object to build. And that question pushed the entire project to the edge of feasibility, where solving one problem meant creating another, and choosing the wrong compromise could make the structure impossible to complete, operate, or justify. This was the point where many megaprojects quietly stop. This one didn't. By this stage, the greatest danger was no longer dramatic collapse. It was something quieter, slower, harder to detect. Engineers were not afraid that the structure would fail suddenly. They feared it would drift out of tolerance, one fraction of a millimeter at a time. The entire system depended on artificial islands acting as transition points between bridge and open water. Unlike bedrock, these islands were engineered ground, assembled layer by layer, compacted under strict control. But even with perfect execution, they would never behave identically. That difference mattered. If one island settled slightly more than another, loads would no longer distribute evenly. Forces would begin to migrate, concentrating where the structure was stiffest instead of where it was strongest. Over time, that imbalance could propagate through the entire system. This is differential settlement, not a failure event, but a process. Above it, the bridge would continue to move, not visibly, not dramatically, but constantly. Wind, temperature change, traffic loads, tidal variation, each introduced micro-movements that never fully disappeared. Every joint absorbed them. Every connection flexed, then returned. And over millions of cycles, those movements accumulated fatigue. Nothing would snap. Nothing would give way. The structure would simply age faster than expected. And then there was the most feared scenario of all: alignment. In a project this long, with multiple construction zones operating independently, alignment errors are unavoidable. The danger wasn't making them, it was locking them in. If a segment connected too rigidly too early, it could prevent adjacent sections from accommodating natural movement. Instead of flexing together, parts of the structure would begin resisting each other. like a door installed perfectly straight in a building that continues to settle. At that point, correction becomes impossible without dismantling completed work. This is the chain failure engineers feared most. A system that remains standing, fully loaded, and outwardly intact, while internal stresses quietly climb beyond what it was ever designed to endure. Avoiding that outcome required more than strength. It required a level of coordination, tolerance control, and behavioral prediction that few projects ever attempt. And it forced one final question into the open. If surface structures could not guarantee alignment, flexibility, and long-term stability, what if the most critical part of the crossing didn't sit above the sea at all? The solution did not emerge from improving bridge design. It emerged from abandoning the idea that the entire crossing had to remain above the sea. Engineers reached a conclusion that would have seemed illogical at the start of the project. The safest way to cross the busiest shipping corridor was not to rise over it, but to disappear beneath it. This is where the project stopped being a bridge in the conventional sense. Instead of forcing massive spans to coexist with global maritime traffic, the most critical section of the crossing was transformed into an immersed tunnel, something no bridge project had ever attempted at this scale under these conditions. The logic was precise. Below the seabed, wind becomes irrelevant. Ship collision risk drops to zero. Wave-induced motion vanishes. But this solution replaced one set of dangers with another. Each tunnel segment was a rigid structure, built elsewhere, transported by sea, and lowered into a prepared trench on the ocean floor. Ocean currents did not stop for alignment. Tides did not pause for precision. Every placement had to occur within extremely narrow windows where environmental forces briefly aligned in the engineer's favor. Once a segment was lowered, there was no second attempt. Alignment tolerances were measured in millimeters. Errors could not be absorbed later, they would propagate forward, locking geometry into place. What made the system viable was not the tunnel alone, but the way it connected to everything else. Artificial islands were no longer just supports. They became transition machines, structures designed to absorb movement from the bridge, stiffness from the tunnel, and settlement from the seabed, without allowing stress to concentrate at any single interface. The bridge deck could flex, the tunnel could remain rigid. The islands redistributed the difference. Instead of fighting movement, the system managed it. For the first time in the project, bridge, island, and tunnel stopped behaving like separate solutions stitched together under pressure. They began to act as one continuous structure, each part compensating for the weaknesses of the others. This did not eliminate risk, it reorganized it. And it allowed the Hong Kong-Zhuhai Macau Bridge to cross a zone that no surface bridge could ever safely occupy. The impossible crossing was no longer solved by force. It was solved by knowing where not to exist. In the end, the Hong Kong-Zhuhai Macau Bridge did more than connect cities. It redefined how far infrastructure can be pushed before the environment pushes back. This project was not built with comfortable margins. Human risk, technical tolerance, and operational precision were all compressed to levels rarely accepted in civil engineering. Every major decision reduced one danger by amplifying another. Every solution carried a cost that could not be fully eliminated, only managed. There was no moment where the ocean became friendly, only moments where it became briefly controllable. The bridge stands today not because the sea was conquered, but because it was carefully avoided, redirected, and negotiated with. Where forces could not be resisted, they were bypassed. Where movement could not be stopped, it was absorbed. Where surface structures would have imposed global consequences, the infrastructure vanished below the seabed instead. That logic has already influenced how engineers think about future crossings in hostile environments, not as isolated structures, but as hybrid systems, part bridge, part tunnel, part ground engineering, designed to cooperate with forces they cannot dominate. But there is another legacy, quieter and less celebratory. This bridge is also a warning. It shows that building at the edge of feasibility demands absolute discipline, flawless coordination, and acceptance that recovery options may not exist. Once construction begins at this scale and in this environment, retreat is no longer possible. The Hong Kong-Zhuhai Macau crossing proves that the impossible can be built. It also makes something equally clear. When infrastructure is forced into the open ocean, success is not measured by what is achieved, but by how little room is left for error.